When studying infinite sums or series, we often talk about the tail of the series. In this video, I want to explain what this term means and why it is useful. The motivating question is this one. Let's compare these two series, the sum of an as n goes from 0 to infinity and as n goes from 1 to infinity. What's the relation between them? Well, in this case, the answer is going to be the obvious one, and this exactly works as we expect it would work. The second series is the same as the first one, except the first one has one extra term. So what the theorem says is that the first series is convergent, represents a number, even only if the second series is convergent, it represents a number. And moreover, in that case, the value of the first sum is equal to the value of the second sum plus the extra term. Nothing surprising here, this is exactly as we would expect it. I'm not going to write the details of the proof. If you want to write a formal proof for this, it works the same as pretty much all proofs about series. First, write the series, the infinite sum, as a limit of finite sums. Second, use the fact that we know the property to be true for finite sums. And third, pass to the limit. It works nicely, nothing surprising. But I want to introduce a piece of notation. Because this theorem is true, we can write things like this. We can say the sum of an as n goes to infinity is convergent or is divergent, and we don't even specify where it starts. The reason this notation is okay is because it's well defined. If the series starting at 0 is convergent, starting at 1 is convergent, and the same way starting at 2 or at 7 or at any other number. I wrote the theorem only for 0 and 1, but it will be true for any two starting points. So we can use this notation to indicate the series is convergent, it represents a number, and we don't bother saying where it starts. If we want to know the actual value of the sum, then it matters where we start, that will change it. But if we only want to know whether the series is convergent, whether it represents a number, it doesn't matter where we start. How do we capitalize on this? There are many theorems we're going to learn about series, about convergence of series, and many of them have this general form. This is sort of a template. Some condition implies that the series is convergent. And the condition often has a form like this. If for all natural numbers n, some property, that I'm writing in red here, this is generic, if for all natural numbers n, some property is true, then the series must be convergent. There are many versions of this theorem with different properties. Well, because of what I just explained about the series being convergent no matter where we start, if we have proven a theorem like this, then we immediately have a more general theorem. And instead of saying for all natural numbers n, I can obtain the same conclusion if the red property is only true for all large values of n. The precise definition of for all large values of n is for all values of n starting at 1, or more formally, if there exists a natural number n sub 0 such that the property in red is true for n sub 0 and for all natural numbers afterwards. This is just a formal way to say for all large values of n. In summary, whenever we get a theorem like the first one, which will probably be simpler to write and state and prove, we immediately for free get a second theorem, like the second one here, which is more general, and it's going to be more applicable and more helpful in examples, and we don't have to prove it explicitly. This will come in handy, and this is why we like to talk about the tail of a series. When it comes to convergence of a series, the only thing that matters is what happens for large values of n.